Hey there, I'm so proud of you. You made it to probably one of the most important videos of the year, which is the fundamental theorem of calculus, the second part. This theorem is so important. It's just such a great human achievement as far as mathematics is concerned. And this theorem is going to connect everything we knew about derivatives and integrals, everything we know about change and area. Is all going to come together in this second part of the fundamental theorem of calculus. And you're going to use this theorem all the time from now on. It'll form the foundation for everything that you do in calculus going forward. And that's not an understatement. That's why it's called the fundamental theorem. Duh. So let's introduce this theorem for you. If your teacher's been smart, he's been kind of giving you some hints as to where this theorem is going to go. And basically it just says if f is a continuous function on the closed interval a to b, then the integral from a to b of f of x dx equals capital F of b minus capital F of a. And yes, I'm pronouncing that capital F. Capital F is any antiderivative of f. In other words, an antiderivative is a function such that capital F prime is equal to f. All right, so the derivative of capital F is little f. It's the function inside the integral. So how do you prove this? Well, it's actually a relatively easy proof if you have the first part of the FTC. And we had discovered in a previous video that capital F of x, as defined as the integral from a to x of f of t dt, is what we call an antiderivative of f, all right? It's kind of the simplest way, really, to write an antiderivative of little f. And so what that means is if I want to evaluate capital F of b minus capital F of a, all I have to do is plug in b and a in for x here. So this statement, capital F of b minus capital F of a, is the integral from a to b of f of t dt minus the integral from a to a of f of t dt. And we know the integral from a to a of anything is just 0. So in other words, this integral from a to b of f of t dt is capital F of b minus capital F of a. And it comes right from that first part of the FTC. This is so important, though, we're going to distinguish it with its own video, and you're going to see all this throughout the rest of your career. So let's see this in action here. We got the integral from 1 to 4 of x squared dx. Right? So 3 steps I'm going to lead you through to actually find the value of this integral, and they're all going to involve finding an antiderivative and plugging in numbers. So the first step is to find the simplest antiderivative, right, of x squared, and that's simple. It's x cubed over 3. Now you might ask, well, where's the plus c, or where's plus 7, or some other constant? Well, as you'll see in just a second, the constant doesn't matter because what we're going to do is we're going to plug in 4 and 1 into our antiderivative and subtract the two of them. And if we just have a plus 7 here, it's just going to cancel out because you're going to plug in 4, and that doesn't affect the constant, and you're going to subtract what you get when you plug in 1. So you'll see this in action right here. We evaluate the antiderivative at the upper limit and subtract the antiderivative at the lower limit. So as you're setting this up, all right, yes, there's a particular way that you should write this. So x cubed over 3 is the antiderivative, so start with that. And then you'll draw a little bar right here, which indicates that you're going to plug in limits. So we have a lower limit of 1, upper limit of 4. The upper limit, f of b, all right, always gets plugged in first. So we go 4 cubed over 3 minus 1 cubed over 3. And that's it. After that, all you got to do is just evaluate. Right, so once I plug that in, I find out that 4 cubed is 64, divided by 3, minus 1/3. And then if I subtract the two of them, and we get 21 as our final answer. And what this says is the area, the signed area in particular between y equals x squared and the x-axis is 21 units squared. All right, so you got to find an antiderivative. That's why we've been practicing so much with them. All right, and plug in your upper limit, subtract what you get when you plug in your lower limit, and solve. So in this case, we got 21. So right here, notice, by the way, if I had said x cubed over 3 plus 1, for example, I would have added 1 here, but subtracted 1 here. All right, and so they would just cancel out. So we always want to choose the simplest antiderivative where c is 0. All right, let's try another one. The integral from 1 to 3 of dx over x squared, which just for our sake, I'll rewrite this as the integral from 1 to 3 of x to the negative 2 dx. We find our simplest antiderivative, which will be negative x to the negative first, or negative 1 over x. Okay, notice no plus c. We don't need it. We just need the plus c to be 0 here. Now we evaluate the antiderivative at the upper limit, subtract the antiderivative at the lower limit. So the upper limit is 3, so I plug that in first at the top. So I get negative 1/3 minus a negative 1, which ends up being a plus 1 altogether. So we get a 1 minus a third, which is 2/3. All we've done is we find the signed area between 1 over x squared and the x-axis, and that is 2/3 units squared. Okay, let's take a look at some quick examples here. Now that you have the idea of what we're doing and the notation that we're using, let's say we wanted to find the integral from 0 to 2 of e to the x dx. The simplest antiderivative of e to the x is e to the x. So we put that right here, put a little bar there that shows we're going to plug in 2 first and then 0. When I plug in 2, I get e squared. When I plug in 0, I get e to the 0, which is 1. And that's it. That's your final answer. How simple is this? Really, the tricky part is actually finding the antiderivative, and sometimes it's evaluating it. You have to actually find values of like sine of pi over 4 or e squared or that sort of thing. But for now, that's the answer. That's it. You leave it like that. All right, so the integral from negative e squared to negative 1 of dx over x. So remember the antiderivative of this, which is 1 over x dx, we call natural log of absolute value of x. And now hopefully we can see why it's important that we put absolute value on here, because we want a really powerful antiderivative. And this powerful antiderivative will allow us to plug in negative numbers. All right, so we plug in negative 1, and we get natural log of the absolute value of negative 1, which will eventually be positive here. And then we get the natural log of the absolute value of negative e squared. The natural log of the absolute value of negative 1 is just 0, because natural log of 1 is 0. And then the natural log of e squared, once we make this into a positive, is just 2. So 0 minus 2 gives us negative 2. The integral from pi over 4, 3 pi over 4 of cosecant of theta times cotangent of theta d theta. So we find our simplest antiderivative of this, which would be negative cosecant squared theta. We plug in 3 pi over 4 and pi over 4, and as it turns out, cosecant squared of theta is the same value at each of these. Basically, cosecant is 1 over sine, and sine at pi over 4 and 3 pi over 4 is the same value. So when I subtract the two of these, I end up with 0 as my final answer. And here's a little more complicated one. We've got the integral from 0 to 1 of 1 plus 1/2 u to the 4th minus 2/5 u to the 9th du. All right, so again, I try to find my simplest antiderivative. So I get u plus u to the 5th over 10. So I went up a power, divide by my new power. There's my new antiderivative, minus u to the 10th over 25. And now I need to plug in 1. And remember, I need to plug it in every single spot I see u. We'll practice more of this with the notation and what I suggest that you do if you see multiple terms like this. But we're going to get a 1 plus a 1/10 minus a 1 over 25. And then minus everything we get when we plug in 0 into this, which is just going to be 0 overall. And this simplifies to 53 over 50. We're going to practice these a lot in class, but I want you to kind of get the idea and have an idea of what's happening before we go forward. Okay. Another thing that you're going to see is what I'm going to call the magic carpet from now on. All right, magic carpet, because the integral looks like a little, the magic carpet that you see in a popular Disney movie, not to be mentioned. So in this case, all right, basically, if you remember, the integral from a to b of little f of x dx is capital F of b minus capital F of a. And we can actually add capital F of a to both sides, and we get this statement right here. And this statement is often a whole lot more useful than the other statement. The reason why is because if you want to get to capital F of b, if you want to find that value, all you need to do is take where you're starting, capital F of a, and add the integral from a to b of little f of x dx. This is like traveling on the magic carpet. All right, so take where you start, travel on that magic carpet, and then you'll get to where you want to get. So that's capital F of b. What does that mean? Well, let's say, for example, time is continuous on the closed interval 1 to 4. We know, based on FTC, that this is the integral from 1 to 4 of f prime of x dx is equal to the antiderivative of f prime, which is just f, at 4 minus the f at 1. So this is another statement of FTC. In this case, all right, the derivative f prime's antiderivative is just the original function f. All right. What I'm saying is, if we want to use this magic carpet technique, all right, we can find f of 4 by saying that's just f of 1 plus the integral from 1 to 4 of f prime of x dx. So this is one way that we can go about solving for mysterious values of a function. So as an example, suppose f prime of x is equal to x squared, f of 3 is equal to 5. Can we figure out what f of 4 is really quickly? So yes, you can find an antiderivative, you can use your initial condition, but that's essentially what we're doing right here. So according to this statement, magic carpet, right, f of 4 is just f of 3 plus the integral from 3 to 4. So take where you're starting, that'll be your lower limit. So we started at 3. It's always your initial condition that tells you where to start. So x equals 3, all right, and we're going to start at the y equal to 5. So we would say f of 3 plus 3 integral from 3 to 4 of f prime of x dx. We know f of 3 is equal to 5, so we plug that in. And now we just need to find out what the integral from 3 to 4 of f prime of x dx is. Well, you know, all right, the antiderivative of x squared is x cubed over 3. And then just like before, we would plug in 4 for x, and then subtract what we get when we plug in 3 for x. And we end up with 52 over 3. Okay, so this magic carpet method will help us find missing values as we go forward in a way that's often much faster than finding a whole antiderivative. Here's another example of that. So suppose that y dt is equal to sine squared of t e to the t, and y of 1 is equal to 4. What is y of 0? Well, if you look at this, you're probably frightened because you're like, what in the world do I do to find the antiderivative of this? And the answer is, don't worry. Because on a question like this, you'll have access to a calculator, all right? And just as a little reminder, when we went through and we did definite integrals, there was a nice button on your calculator to actually help you find antiderivatives, right? And that is our good old friend, math number 9, right? So let me show you what's going on with this. So if I wanted to find y of 0 is just y of 1, right? So our initial condition, plus the integral from 1 to 0. So remember, you always want to start at what your condition gives you. So we go from 1 to 0 of dy dt dt. I know that looks weird, right? But eventually what the idea is that we're going to take y of 1, which was equal to 4, and we're going to add the integral, that's math number 9, so math number 9 right down here, the integral from 1 to 0 of sine squared x times e to the x, or you can use t's as well, but I'm going to use x's here, right? So then I would make sure to square my sine function, and when I do so, I'm going to end up with 3.544. Okay, so math number 9 is another useful tool to help us evaluate according to the FTC, but right here, FTC is used because we're adding our initial condition to what happens on the magic carpet. Okay, last example here, and I'm going to briefly go over this and talk more about this in class. But what do you do if you have to do a substitution? So in this case, we've got the integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. And the answer is, well, your limits, just like everything else in the integral, is all in terms of x. That, in fact, is what the dx helps to tell you, is that the limits start at x equals 0 and go to x equal to 2. If you remember, when you do a substitution, you look for an inside function. So u is equal to x cubed plus 1, which I'm not going to go over all the details here, but basically, eventually that means that dx is equal to du over 3x squared. So this is all in a previous video. When I substitute, all right, I end up, after I simplify, I get the integral from 0 to 2 of du over 3 times the square root of u. Now, something's not right here. Your x limits are in terms of, or your limits are in terms of x, but everything else is in terms of u. So if you're going to solve this problem, we need to change our limits also to be in terms of u. Everything needs to go and be changed in terms of u. So luckily, we've created an equation that relates x and u. U is equal to x cubed plus 1. So for example, when x is equal to u, or 0, u is equal to 1. I just plug that right into my formula right here. When x equals 2, 2 cubed plus 1 means that u is equal to 9. But technically, this limit means that we go from u equals 1 to u equals 9 of 1/3 times the square root of u du. And when we solve everything now in terms of u. So 2/3 u to the 3/2 from 1 to 9. Plug that in and you get 52 over 3. We're going to practice more of that in class as we go along, but the idea is you want to change your limits in addition to everything else in terms of u. So in summary, you're going to use this FTC Part 2 all the time. Just get ready. It'll be your friend. And rewriting the FTC statement, with the magic carpet also gained you some information, as does rewriting the limits and a substitution. Thank you so much. See you again soon.